Hello everyone, hope all are well. Today we will be discussing about our project Beat Estimation from Musicians' Visual Cues. I would like to thank Senem, William and my supervisor Dr. Joseph TIMONEY for collaborating in this work. I am a third year PhD student at Maynooth University, Ireland. Music offers an unique abstract way for expression of human emotions and mood, wherein melodic harmony is achieved through a blend of pitch, rhythm, tempo, texture, and other sonic qualities. When we listen to musical performance, our mind subconsciously starts participating in it. Audience like us can be seen to respond by tapping our feet or clapping our hands or by nodding our heads. Musicians also move their body in different ways to perform expressive pieces depending upon their instrument they are playing. One of the major characteristics of such multi-ensemble topologies is that the musicians do not engage with rigidity, rather they move, play, and act as they feel. Further, the role of different musicians in an orchestra changes following a rhythm. They try to communicate in real time with each other through nonverbal gestures or by principal conductor. Thus, there is a smooth transition of musician's role from leader and follower. Rhythm is also present in dance. One of the core tasks of dance information retrieval is to extract high level of semantics from dance videos, which could be similar to what music information retrieval tasks attempt to detect from music. Movements are more prominent in dance and performances are always synchronized. Similarly, in large musical ensembles, the conductor is present. He controls the pace of the music of the ensemble and also maintains the expression of the performance. We can see a time varying leader follower relationship during the whole performance. But the work becomes tough when there is no musical conductor. There is a lot of practice needed for musicians. Now let's try a small example where we play a video of musicians playing a particular music performance, and let's see that our brain can predict the beat from those visuals or not. I hope you try to predict the beats, but as we see that it is a tough job, right? Thus, this work aims to discover a robust technique to identify musical phase or beats through visual cues derived from musicians' body movement. For understanding this dynamics, we use the URMP dataset, which has the audiovisual analysis of musical performances. The dataset comprises of a number of multiple instruments, musical pieces assembled and recorded with individual tracks. For each piece, they provided the musical score in MIDI format, the high quality individual instrument recordings, and the video. This multi-modal dataset had four kinds of performances. It had 11 duets, 12 trios, 14 quartets, and 7 quintets. There were 14 different kinds of string, wind, and brass instruments present in the dataset, which was very useful for our experiment. Another added advantage was all the data were classical pieces, so they had time varying tempo and changing leadership attributes in them. So we can say that this dataset is perfect for our research. So we try to analyze the connection between the musician body movements and the associated audio rhythms, and also try to evaluate the performance using two different approaches to predict the rhythmic phase from multiple musicians' body movements. To understand the musical phases, the time of the audio beats are very important. The audio beats are considered as the ground truth value in the experiment. To compute the audio beats, an audio MIDI alignment technique was used. The MIDI file representation was first converted into its equivalent audio as shown in the figure. Dynamic time wrapping was applied to effectively match and align the audio recordings with the corresponding MIDI transcriptions, after which the beats were estimated from the aligned MIDI information. This process was repeated for the whole dataset. For converting the video into signals to determine the motion, we used two approaches. The first one was the Motiongram and the second was the pose estimation. Let's see what is Motiongram. The Motiongram is created by calculating the spatiotemporal motion using the average pixel intensity change between frames of the video. The horizontal motion is denoted by X, the vertical motion is denoted by Y, and the quantity of motion here was denoted by Z. This was extracted from each videos. It provided a series of images showing in the motion in 2 dimensions across the image plane. This signals was normalized independently for further processing. In the slide, you can see the diagram where we show the relationship between X, Y, and Z signals and the location of the musical beats, and the number of signals in the motiongram is always independent of the number of participants in the video. For pose estimation, we used a library called OpenPose, an improved and robust model for pose estimation that applies path affinity field to predict the key points for multiple humans. Two different approaches were tested for pose estimation. They are the first frame as reference and spatial derivative of key points. Let's know them in details. We consider each musician as an independent oscillator. In the first technique, the first frame was considered as the point of reference for calculating the motion. These coordinates were used to compute the full body motion of each musician. It generated 17 body key points from each frames. The inter-key point distance of each individual was recorded over time from their body centers. An average value was computed to find the relative motion resulting in 1D signal for each musician as shown in the figure. As a result, we can say that if there is an increase in number of participants, there will be more signals present for computational consideration. The spatial derivative was used in the second technique to generate the average motion signal of each individual by comparing each frame's key point with its previous frame, similar to optical flow. Given that the points had already been localized, so there was no need to calculate the intensity based on image gradient. After we get the 1D movement signals, we used a AKTA filter for smoothing the signals and then used 5 different decomposition algorithms for signal multiplexing. For each resulting signals, we used a peak detection technique to find the peak and the valley for each algorithm. Then we created a trust value based on the timestamp. For example, if 3 out of the 5 algorithms said that there is a peak or valley in that particular beat, then we consider that to be a beat point. So for evaluation, we selected 3 video files from each 4 type of performances which were not used for training. The classical pieces were mostly composed by famous composers like Holst, Mozart, Joplin, Bach, and others. We observed that we were able to estimate the audio beats from the multiple musicians' body movements. On further observation, we saw that Motiongram was working well with the instruments which had prominent movements like the string instruments, while the spatial derivative approach with pose estimation worked well for wind instruments and other smaller movements instruments. Here is a quick demo of the estimation we have done on the performance. Thus, we can conclude that audio phase estimation can be possible from musicians or multiple musicians' body sway. Estimation technique depends upon the musical instruments. Considering musician as independent oscillator approach is very useful for addressing this kind of problem with pose estimation. For future work, a better post-processing technique should be introduced, keeping in mind the possibility of changing tempo, and include the audio and the video both for beat prediction will give us much better output. And also machine learning technique for predictions can be useful in this kind of scenario. Thank you.